I'm Rishabh, and I'll be talking about robust and composable device-independent protocol for oblivious transfer using fully untrusted quantum devices in the bounded storage model. And this is joint work with my co-authors Shayantan Chakravarti, Rahul Jain, and Upendra Kapshikar. So quantum cryptography allows us to do tasks that may not be possible classically, for example, QKD. So one problem is that for the parties performing quantum operations may not be able to manufacture their own quantum devices. So they may just be classical parties that want to use quantum devices. So one thing that they can do is source them from an external manufacturer. But the problem is the manufacturer could be adversarial. So the framework of device-independent cryptography tries to give protocols that are secure, even when quantum devices are adversarial and can be arbitrarily manipulated by the adversary. So a motivation for this could be, there could be two banks who want to do a cryptographic protocol, but the problem is that the banks may be classical, they don't have quantum labs, but they may want to use quantum resources to do some cryptographic protocol. So the banks can source quantum devices from a third-party vendor, but the problem is that the vendor could be colluding with one of the banks. So the banks would want to test the devices and only go through with the protocol if the devices pass the test. And as I mentioned, the banks, if they're classical, they'll interact with the devices by giving classical inputs and getting classical outputs. So what is oblivious transfer? So oblivious transfer is a fundamental primitive in two-party distrustful cryptography where both parties do not trust each other. And oblivious transfer can be used to securely compute any multi-party functionality, including bit commitment. So in a protocol for oblivious transfer, Alice gets as input two bits S0 and S1, and Bob gets one bit B. So what we want is that at the end of the protocol, Bob gets, so B is the choice bit of Bob. So at the end of the protocol, Bob can get to know about SB, but the security guarantee is that Bob does not know anything about the other bit. And similarly, Alice should not be able to get any information about Bob's choice bit B. So information theoretically, protocols for OT are not possible even with quantum devices. So protocols are for oblivious transfer are usually considered under different bounds on the adversaries. So one popular setting is of time-bounded adversaries, where we assume something like a one-way function or hardness of the LWE problem, and then try to build protocols using that. A practically motivated setting is the bounded quantum storage model, where the devices and parties have bounded long-term quantum memory. So there's a delay in the protocol, which is a fixed time interval, and after that delay, only a bounded amount of quantum memory is left with any party. And this is a practical assumption, as NISQ devices usually don't have, NISQ devices do not have long-term quantum memory. So because the devices are adversarial, device-independent protocols require testing of the devices to be done. So the typical way in which we do this is we play a non-local game with devices, which could be adversarial, so that states and measurements are unknown. And if we are able to achieve a winning probability for the game that is close to the optimal winning probability, then rigidity would tell us that the states and measurements of the devices are close to those in an ideal non-local game. So a quick comparison between device-independent quantum key distribution and oblivious transfer. So in DIQKD, Alice and Bob are honest devices. So Alice and Bob can play the non-local game properly in the sense that Alice and Bob can at least input the correct distribution of the questions during the testing. And testing of devices becomes possible in QKD, and there's a lot of literature. But in case of oblivious transfer, Alice and Bob do not trust each other. So Alice and Bob could also be cheating during the testing of the non-local game. So they may input like arbitrary distributions during the testing part, which may not lead to, which will not give us security guarantees like rigidity. So here testing of devices is not obvious, and there's very limited literature in DI two-party cryptography. And most of these works have the IID assumption on the devices, which is like if you use multiple devices, then each of them are independent and the devices are identical. And this is not a justified assumption in practice because the devices are adversarial and could be created by one of the cheating parties themselves. So yeah, we use something called a magic square game or magic square device. So in an ideal magic square device, Alice and Bob input X and Y randomly from 0, 1, and 2. So Alice selects basically a random row of this 3 by 3 square, and Bob selects some random column. So the guarantee that we have is row parities are 0 and column parities are 1. So Alice gets as output a string with parity 0. Bob gets as output a string with parity 1. And the guarantee that we want is that the common bit is the same, which means the common bit at the intersection of Alice's row and Bob's column should be the same. And what we know is that this game can be won with probability at most 8/9 in the classical case. But if we use quantum devices, we can win this with probability 1. And so other than the common bit, in an ideal magic square game, any uncommon bit is completely uniform to the other party. So yeah, Alice's uncommon bits are completely random to Bob and vice versa. So yeah, what we present a protocol for oblivious transfer with the following properties and assumptions. So we have device independence, which means honest Alice and Bob could be classical parties that are interacting with quantum devices that are untrusted. The adversary can design all the devices together before the protocol starts in any non-IID manner. So there could be joint attacks happening on the states and measurements of the devices. And no other device-independent two-party protocols like for OT allow such a general non-IID adversary. Our protocol uses magic square devices, which can be assumed to be implementable in the NISQ era. So the protocol is efficient in the sense that if lambda is the security parameter, then to get negligible in lambda correctness and security errors, we require only polylog lambda running time and polylog number of devices. Our protocol is robust, which means that the protocol between honest parties should work correctly, even when there could be small manufacturing errors on the devices, which is also a practically motivated property. So we also provide composable security, which means that if our protocol is used as a building block inside a larger protocol, even then the security guarantee should hold. And we provide simulator-based security for that, and then also prove a sequential composition theorem for that. And none of the earlier device-independent oblivious transfer protocols are also composable. So our assumptions are, as I said, the bounded quantum storage model. So after delay, the quantum memory of any party is linearly upper bounded in the number of devices. So other than the bounded quantum storage assumption, there's no other assumption on the adversary. So the adversary could have unbounded classical and quantum computational power. And another thing is that once the protocol starts, the communication between Alice's and Bob's parts of the shared devices should be linearly upper bounded in the number of devices. So this is also what is called leakage. So we allow for linear leakage between the devices. Yeah, so this is roughly the protocol. So we have a protocol between Alice and Bob. Alice gets as input 2 bits S0 and S1. Bob gets choice bit D. So we initially, there's a test phase happening. And so, okay, I'll describe more about this in the coming slides. But so there's a test phase, and after the test phase, Alice inputs random X to her part of the magic square devices, while Bob enters D in all the magic square devices. And after that, there's a test phase check and if the check passes, only then we go through with the protocol, which is described below. So what happens is, yeah, at the beginning of the protocol, there's a test phase where Alice selects a random and large enough subset of devices to test the magic square game. So if the test passes, what Alice does is she uses random bits from the first two columns of the output of her magic square devices to obfuscate S0 and S1. So as follows. So A0 represents the first bit, and A0 and A1 represent the first two columns of the output of Alice, and she uses those to do a one-time pad. So yeah, so Alice then would sample two strings T0 and T1, which will act as seeds for a strong seeded extractor. I'll not get into much details about this, but basically what an extractor does is it converts a weakly random source with some min entropy to a uniform output. So the output of the extractor is used to hide SB as like a one-time pad. So Alice extracts the first column, like uses the extractor to get one bit and then does an XOR. So it does a one-time pad on S0 and S1. And so we want robustness, which means like when Alice and Bob are honest, but the devices may not be completely ideal, even then the protocol should work. So for that, suppose like D is equal to 0. So in that case, using the common bit property of the magic square game, we would get that B of X is equal to A of 0. And note that X is being sent across during the protocol phase, so after the delay. So if Bob has X, then Bob will be able to compute A0, which would be equal to B of X, and hence recover S0 by like computing this extractor output and then doing an XOR. So basically computing the same one-time pad. So what we have is that the test phase guarantees that if the devices are far from an ideal device, then the protocol will abort. But if the test phase passes, then on a randomly new index outside the testing block, the magic square game will pass with high probability. So if the devices were not ideal, but the test phase passes, then with high probability, B of X will be close to A of 0, but not exactly equal. So we use an error correcting code that allows Bob to recover A0 from B of X. And for that, we send across W0 and W1, which are syndromes for where H is a parity check matrix for a appropriately chosen code. Yeah, so yeah, we also want sender security and receiver security. So for receiver security, it's relatively easier as compared to sender security. So for receiver security, the guarantee that we have is the communication between Alice and Bob in the test phase is actually independent of Bob's choice bit D. And after the test phase, there's no communication from Bob to Alice, as we can see in the protocol. So this guarantees that Alice does not get any information about Bob's choice bit D. For sender security, we do a more, it will require more analysis using a parallel repetition theorem. So for sender security, what we require is that a cheating Bob should not be able to guess both S0 and S1. So since we use the extractor to hide the bits, what we basically need to show that there's min entropy in either A0 or A1 given all bits of Bob. So how we do is, we construct a single copy game, which is actually a classical quantum hybrid game because that takes care of the delay in the protocol. So after the delay, there's a decoherence of states happening and things become classical. So basically in G1, what we do is with probability, some constant probability delta, testing of devices happens where the magic square predicate is checked. So this corresponds to the test phase in the actual protocol. And otherwise, Bob needs to guess both of Alice's output bits, so A0 and A1. And what we do is we can bound the maximum probability of winning this single copy game G1. And in this step, the bounded quantum storage is crucial because in our protocol, X is being sent across to Bob after the delay. So if there was no bounded quantum storage and X was sent across, then Bob will be able to win this game with probability 1 actually, without even using quantum resources. So the delay and the bounded quantum storage is essential over here. We then prove a parallel repetition theorem for G1, which says that if we are playing n copies of the game in parallel, then the probability of winning that n copy game is exponentially small in n. So using this, we can show that Bob cannot guess both A0 and A1. So like more formally, given all bits of Bob, there exists a bit d tilde for which the min entropy in A d tilde is large. So d tilde is from 0 and 1. And so if the min entropy is high, then if we apply this extractor on A d tilde, then the extractor basically guarantees us that the output of the extractor is uniform and independent of Bob. So if we use that as a one-time pad, so we were using this extractor output as a one-time pad on SB, right? So if the extractor output is uniform, then Bob cannot guess SD tilde. So Bob's guessing probability for SD tilde is negligible, and this implies the sender security. And yeah, these are some references that I used. Yeah, thank you.
Thank you. Any questions?
Thanks for your presentation. I found that your protocol is based on the ideal magic square games. I wonder if your protocols can tolerate some noise, such as the efficiency or incorrect measurement.
Yeah, so that is something along what I said about robustness. So our protocol actually does not require ideal magic square devices, and so robustness basically guarantees if Alice and Bob are honest, but the devices may not be completely ideal, but are like close to ideal, like some noise in the devices. Then even then, like using this error correcting code and like this testing phase, we can show that the protocol works even in that case. So that is what robustness of the protocol guarantees.
Is there a threshold of the noise?
Theoretical noise. Like we have so it's just about how far the device is from an ideal device. So you can model the whatever noise you want and then see how far that leads. Like so, if there's noise, then the device will not be ideal, right? It will be far from an ideal device. So so the robustness will depend on how far that device is from an ideal device. So yeah, using like the common noise models, we can actually guarantee robustness depending on other parameters.
Okay, thanks.
Thank you for the nice talk. I want to ask you if you have a comparison with already other protocol in terms of key rate or other kind of figure of merit.
Sorry.
If you have a comparison with the already established result with this new idea.
Yeah. So like I had described briefly, like there's no other protocol that actually works against non-IID attacks in the bounded storage model. So this is the first work that actually does that. So there's no direct comparison because most other works require either IID assumption on the devices or like they don't have security in terms of like security parameter. So security is not negligible in the security parameter. And there's some other things also, like none of the other device independent protocols were composable. So none of them were given in the simulator based model. So like there are a lot of things that we do that have not been done like earlier. So there's no like direct comparison in that sense.